All right, let's dive in. Today, we're basically becoming geological detectives. We're heading out on a huge treasure hunt deep into the Earth's crust, and we're looking for the very specific, and actually pretty rare, conditions that create what we call black gold, or petroleum. So, yeah, grab your virtual hard hat, let's get digging.
Okay, first things first, we've got to bust a huge myth. When you hear the term oil reservoir, your brain probably pictures some giant underground cave, right? A huge lake of oil just sloshing around down there. But that's not it at all. The reality is way more subtle and, honestly, a lot cooler. The treasure isn't sitting in a big open chest, it's literally locked inside the rock itself.
So, that means our first job on this geological hunt is to find the right neighborhood, the perfect home for these hydrocarbons. And that means we have to find the right kind of rock, because not just any old rock is going to work.
Now take a look at this. This is where things get really interesting. A massive 95% of the Earth's crust is igneous rock. We're talking granite, the stuff born from cooled magma. But the prize we're looking for? It's almost always found in that tiny little 5% slice. That slice is made of sedimentary and metamorphic rocks. We are truly looking for a needle in a geological haystack here.
And this slide really shows you why. Over on the right, you've got those igneous and metamorphic rocks. See how dense and tightly packed they are? They're basically a solid barrier. But then look to the left at the sedimentary rocks. These are different. They're formed from little bits and pieces of older rocks, sand, silt, organic stuff, all squeezed together over millions of years. And the key thing is, they have little tiny spaces between all those bits. They are porous hosts. And that is exactly what we need.
But, just finding any sedimentary rock isn't going to cut it. We need a really special kind, one that acts like a top-quality sponge. A sponge that can both hold on to the oil and, crucially, let it flow out. And for that to happen, it needs two critical properties.
The first property is called porosity. The easiest way to think about it is just storage space. It's the percentage of that rock that is just empty space, these tiny little pores. So, the higher the porosity, the more oil and gas the rock can possibly hold. Simple as that.
But having a ton of storage space is totally useless if you can't get anything in or out of it, right? And that's where the second property comes in, permeability. This is all about how connected those little pores are. It's the network of pathways, the plumbing, that lets the oil and gas actually flow through the rock and towards a well.
So here's the bottom line, the thing you absolutely have to remember. You need both. It's no good having one without the other. Think of it like a block of Swiss cheese. All those holes give it really high porosity, lots of storage. But if none of those holes are connected to each other, well, you've got super low permeability and nothing can flow through it. For oil to be something we can actually get out of the ground, the rock needs both high porosity and high permeability, lots of storage and lots of well-connected pathways.
Okay, so let's say we did it. We found our perfect rock sponge, and it's full of oil. Awesome. But there's a huge problem. Oil and gas are way less dense than the water that's also in the rock, so they're always trying to float up, to migrate towards the surface. Without something to stop them, they would have just escaped millions of years ago. We need a trap.
And luckily for us, geology has some pretty clever ways to lock this treasure in place. As you can see here, these are the main kinds of traps that geologists are hunting for. They're all just different kinds of geological structures where our porous, permeable rock gets sealed off by a rock layer that's impermeable. It acts like a lid on a jar. The most common ones you hear about are anticlines, which are these big upward folds, and faults, which are massive cracks in the rock.
Let's look at a real classic, an anticline. It's basically an upward arch in the rock layers. So as the oil and gas are migrating up through their porous layer, they hit this arch and get stuck at the very top, at the peak. They can't get through the impermeable cap rock above them. It's just like trapping air under an upside-down bowl in water. This is probably the most common and historically important type of trap there is.
Another really common trap is formed by a fault. Now, a fault is a huge crack where entire layers of rock have shifted and moved. If that movement slides our porous reservoir rock right up against a solid, dense, impermeable layer, boom, it's a dead end. The migration path is completely blocked and the oil and gas just pile up right there against the fault line.
So we have our porous rock, and we have our trap to hold everything in place. We are so close. But there are two final environmental factors that are absolutely critical: the insane heat and pressure you find deep inside the Earth. This is the kitchen. This is where the hydrocarbons actually get cooked into existence.
And the pressure down there is just crushing. I mean, in a perfectly sealed-off trap, you have the weight of miles of rock above,
what geologists call the overburden, and it's all pressing down directly on the fluids. This can create what's known as abnormal pressure, sometimes almost double what you'd expect at that depth. And for geologists, that's a really critical piece of the puzzle. And man, it gets hot, and it gets hot fast. For every 100 feet you go deeper into the Earth, the temperature goes up by about 1.6 degrees Fahrenheit. They call this the geothermal gradient, and it's this constant, sustained heat over millions and millions of years that cooks the buried organic material and transforms it into the oil and gas we're searching for. So, we've gathered all of our ingredients. We've got the right kind of rock with the right properties, we've got the right kind of structure to trap it all, and we have the right cooking conditions. Now let's put it all together. Let's look at the perfect geologic recipe.
And here it is, the complete treasure map for finding oil. First, you have to start in a sedimentary basin. Then, you find a rock inside it that has high porosity for storage, and you mix in high permeability for flow. Step 4, you make sure it's completely sealed by a geological trap, like an anticline or a fault. And then, the final step, you have to make sure it's been cooked at the right temperature and pressure for millions of years. You get all 5 of those things right, and you just might have found yourself a commercial oil reservoir.
And that kind of brings us to our final thought for today. For more than a century now, we've been hunting for these perfect geological setups, these classic traps. But the thing is, the easy ones, the obvious ones, well, they've mostly been found. And that raises a really critical question for the future of energy. What do you do, and where do you even look, when all the easy-to-find treasure chests are empty? That's the real challenge for the next generation of geological detectives to solve. Thanks for joining us.